At the very edge of our observable universe lies one of the most profound mysteries in modern astronomy. For decades, scientists believed they understood the fundamental nature of cosmic motion, that the universe expands uniformly in all directions, with matter distributed evenly across the vast expanse of space. However, in 2008, a discovery emerged that challenged everything we thought we knew about the cosmos. NASA researchers analyzing data from advanced space telescopes discovered something unprecedented. Hundreds of galaxy clusters moving in unison toward a specific region of space, as if pulled by an invisible force of unimaginable magnitude. This phenomenon, known as dark flow, suggests the presence of something massive lurking beyond the edge of our observable universe, something so enormous it can influence the motion of galaxies across billions of light years. The observable universe boundary. To understand the significance of this discovery, we must first grasp what defines the edge of our observable universe. This boundary represents the furthest point from which light has had time to reach us since the Big Bang occurred approximately 13.8 billion years ago. Beyond this cosmic horizon lies a region that remains forever hidden from our view, not because of any physical barrier, but because the expansion of space itself prevents light from these distant regions from ever reaching Earth. This edge creates what scientists call a causal boundary, a point beyond which nothing can influence us, and we can influence nothing in return. The expansion of space in these regions occurs faster than the speed of light, effectively severing all possible connections between our observable universe and whatever lies beyond. This makes the dark flow phenomenon all the more mysterious and scientifically significant. The discovery of dark flow. The story begins with the Wilkinson Microwave Anisotropy Probe, launched by NASA in 2001 to map the cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates all of space. This radiation provides a snapshot of the universe when it was only 380,000 years old, offering crucial insights into its structure and composition. Dr. Alexander Kashlinsky, leading a team at NASA's Goddard Space Flight Center, decided to use this data in an innovative way. By comparing the cosmic microwave background with the motion of galaxy clusters, his team hoped to detect subtle patterns in cosmic movement. They employed a technique called the kinematic Sunyaev-Zeldovich effect, which measures how cosmic background radiation gains energy when passing through moving galaxy clusters. The analysis was extraordinarily challenging, requiring statistical examination of over 1,000 galaxy clusters to detect the incredibly faint signals. What they discovered defied all expectations. A massive bulk flow of galaxy clusters stretching 2.5 billion light-years across space, all moving between 600 to 1,000 kilometers per second in the direction of the constellations Centaurus and Hydra. The implications of cosmic motion. This discovery represents far more than just an interesting astronomical observation. The uniform motion of these galaxy clusters suggests they are responding to a gravitational influence of unprecedented scale. According to our current understanding of physics, such coordinated movement across billions of light years would require a source of gravity so massive it challenges our fundamental assumptions about the universe's structure. The movement appears to violate one of cosmology's core principles, the cosmological principle, which states that the universe is homogeneous and isotropic on large scales. This principle suggests that matter is distributed roughly evenly throughout space, and that there should be no preferred direction of motion when viewing the universe as a whole. Dark flow directly contradicts this assumption by indicating a massive asymmetry in the cosmic distribution of matter. The Great Attractor Connection. While analyzing the dark flow phenomenon, scientists also considered its relationship to known large-scale structures in the universe. The Great Attractor, a gravitational anomaly in the direction of Centaurus and Hydra, has long been known to influence the motion of nearby galaxy clusters, including our own local group containing the Milky Way. However, the great attractor's gravitational influence, while significant on a local scale, cannot account for the vast scope of the dark flow phenomenon. The coordinated motion observed extends far beyond what any known structure could influence, suggesting that either our understanding of cosmic architecture is incomplete or something truly massive exists beyond our observable horizon. Theoretical explanations. Scientists have proposed several theoretical frameworks to explain dark flow, with the most compelling involving cosmic inflation, a period of exponential expansion that occurred in the first fraction of a second after the Big Bang. During this inflationary epoch, the universe expanded faster than the speed of light, smoothing out irregularities and creating the uniform cosmic microwave background we observe today. The dark flow hypothesis suggests that before cosmic inflation began, there existed massive concentrations of matter in what is now the unobservable universe. These structures could have gravitationally influenced our local region of space, imparting momentum to galaxy clusters that persist today. Cosmic inflation then carried these massive attractors far beyond our observable horizon, leaving only their gravitational legacy in the form of the coordinated galactic motion we observe. This explanation requires the existence of structures far more massive and concentrated than current cosmological models predict. Such concentrations would represent a fundamental departure from the uniformity principle that underlies our understanding of cosmic evolution. Scientific controversy and debate. The dark flow discovery has generated significant controversy within the scientific community. While Kashlinsky's team remains confident in their findings, other research groups using different methodologies and datasets have failed to reproduce the results. Most notably, the European Space Agency's Planck satellite, which created an even more detailed map of the cosmic microwave background, found no evidence of the large-scale bulk flow. This disagreement has led to intense scientific debate about methodology, data analysis techniques, and the interpretation of extremely subtle cosmic signals. Some scientists argue that the dark flow signal falls within the margin of error for such complex measurements, while others maintain that the coordinated motion represents a genuine cosmic phenomenon requiring revolutionary changes to our understanding of the universe. Implications for cosmology. If dark flow proves to be real, its implications for cosmology would be profound. It would suggest that our observable universe represents only a small, potentially unrepresentative sample of a much larger cosmic structure. The universe beyond our horizon might be far more complex and varied than we currently imagine, with massive concentrations of matter and energy that dwarf anything we can directly observe. Such a discovery would force scientists to reconsider fundamental assumptions about cosmic homogeneity and the nature of the Big Bang itself. It might indicate that cosmic inflation did not create the uniform universe we observe locally, but rather that we exist in an unusually smooth region of a far more varied cosmic landscape. Current research and future prospects. The debate over dark flow continues as astronomers develop more sophisticated techniques for measuring cosmic motion and analyzing the cosmic microwave background. New space-based observatories and ground-based telescopes promise to provide increasingly precise data that may finally resolve the controversy. Future missions will employ advanced statistical methods and larger datasets to search for evidence of bulk cosmic motion. These efforts represent one of the most important ongoing investigations in modern cosmology, as they may fundamentally alter our understanding of the universe's structure and evolution. The dark flow phenomenon exemplifies the profound mysteries that continue to challenge our understanding of the cosmos. Whether it represents a genuine discovery of massive structures beyond our observable universe or an artifact of complex data analysis, it demonstrates how much we still have to learn about the fundamental nature of reality on the largest scales. This investigation reminds us that the universe may be far stranger and more complex than we currently comprehend. with hidden influences and structures that operate beyond the limits of our direct observation. As technology advances and our analytical methods improve, we may finally determine whether something truly massive lurks at the edge of everything, pulling our cosmic neighborhood toward an unknowable destiny.